All right, we're going to go ahead and get started. Welcome everyone to the Third Coast Water Seminar and our final seminar of the year, Water Quality Modeling and Optimization in Water Distribution Systems, a really important topic that I'm really excited to have on deck. And also just on behalf of all of our convening partners, really want to welcome everyone here, Northwestern, the University of Illinois Urbana-Champaign, Argonne National Laboratory, the University of Chicago, the University of Illinois at Chicago, and all of them coming together under the current banner to bring you this seminar series on a monthly basis all through the year to bring the best of water research from all around the world here for a conversation and some problem solving. And these have been really a wonderful, robust set of discussions through the year. Grateful to have the support of everybody as convening partners and just really looking forward to closing the year strong. So if this happens to be your first Third Coast of welcome, very happy you're joining us. Just a few logistics that are the same every time. We love to have questions from our audience. We have a Q&A tab, and also feel free to use the chat to talk with other participants. We know many of you know each other. It's a great community here at Third Coast. So please feel free to be active and in dialogue. I'll be collecting questions and posing them to our speaker throughout, but just really want to encourage that kind of active participation. And then this event, like all of our Third Coast seminars, is being recorded, and we'll be sharing out the link on Current's event page and on our YouTube channel. So encourage you to subscribe to that if you don't already. It's a great way to catch up on seminars you missed and stay tuned for events that are to come in the future. So our agenda today, here at the Third Coast, we like to keep it focused on the speaker. So we're going to have a wonderful talk from Dr. Ahmed Abokifa, who's the assistant professor in the Department of Civil Materials and Environmental Engineering at the University of Illinois at Chicago. We'll have time for audience Q&A at the end, and then we'll get you out of here right around the top of the hour. And first, just a bit of background on Current and why we're here convening this conversation today. Current's Chicago's Water Innovation Hub. So if you're not familiar with us, we're so excited you're here and getting to know us. We're 5 years old this year, and our job is to really help grow an inclusive blue economy, accelerate innovation, and solve persistent water challenges. Why are we here to do all of that? Well, we all agree we need more healthy water to drink and less flood water in our basements. That's a common challenge for those of us here in the Midwest. It's a common challenge for people around the world. And we also know it's something that affects people really disproportionately. It's a burden that is borne here in the United States by low-income communities and communities of color. And so there's a strong equity agenda to all of this when we think about what it means for all of us to have more healthy water to drink and all of us to have safe, dry homes to live in. We also know that there's a lot of opportunity in water, and we're really excited about the opportunity to create more blue jobs, putting Chicagoans and Illinoisans together to work and building homegrown companies that can help solve water challenges, not only here in our backyard, but around the world. So that's really why Current's here. Our problem statement, as we see it, is that people aren't rallying fast enough behind all of the new ideas and technologies that can help deliver on this promise and potential. We know that innovation is hard. It takes collaboration, and that's why Current exists, to help build partnerships like those represented here at the Third Coast, bringing together people from across disciplines and institutions to try to tackle the types of water challenges that are just too big or too thorny for any one of us to tackle alone. And so those are the kinds of partnerships that Current exists to support and sustain. We're an unbiased advocate for what we see as the best water solutions and policies. So it's our job to scan the horizon and stay on top of technologies that are out there, knowing what's rapidly changing. Third Coast is a really big part of that, trying to understand what's frontier, what's coming out of research universities and our national labs. How can we help assess them, bring them to market faster through pilots and other installations? So beyond the kind of connecting we're doing here, Current also tests technologies in the real world, and we're always building a pipeline of water innovation. So if you're here today to learn, but you have ideas of your own, things you'd love to see tested, let us know. We have a really exciting emerging pipeline of water technologies that we're testing, everything from sewage surveillance to PFAS elimination, things that are applicable, again, not only here in Chicago and our region, but well beyond. So I want to now turn it over to the highlight of the day, our speaker. But to introduce him, I'm going to turn it over to one of our closest collaborators here at Third Coast and one of the founders, Dr. Brian Chaplin from the University of Illinois at Chicago. Brian, over to you to introduce our speaker.
Okay, thanks so much, Elena. And it's my pleasure today to introduce my friend and colleague, Dr. Ahmed Abokifa. Ahmed is an assistant professor in the Civil Materials and Environmental Engineering Department at the University of Illinois at Chicago. Prior to joining UIC in 2020, he was a postdoctoral fellow in Civil, Architectural, and Environmental Engineering Department at UT Austin. He holds a PhD degree in Energy, Environmental, and Chemical Engineering from Washington University in St. Louis, and also BS and MS degrees in Civil Engineering from Cairo University. His research is broadly focused on developing and integrating computational methods at multiple scales and applying these models to understand the behavior of water infrastructures and optimize their performance. So today's talk, he will focus on water distribution systems, where Ahmed will present his team's recent work on optimizing the placement of water quality sensors to maximize network-wide observability of different water quality indicators, and also to enable model predictive water quality control in real time. So we're all very excited about Ahmed's talk, and without further delay, I will turn it over to you, Ahmed.
Thank you, Brian, for the introduction. And I guess thanks for introducing me to Current when I started here at UIC last year. I'm trying to share my screen, but it says I cannot share screen while the other participant is sharing. All right. So can you see my presentation now? Excellent. All right. So good afternoon, everyone. My name is Ahmed Abokifa, and as Brian kindly introduced me, I'm an assistant professor in the Department of Civil Materials and Environmental Engineering here at the University of Illinois at Chicago. I'm also the lead PI of the Smart Water Infrastructure Modeling Research Group. And today I'm going to be talking about water quality, particularly water quality modeling and optimization in drinking water distribution systems. And so it's kind of a well-known fact that as soon as the finished water leaves drinking water treatment plants, the water quality starts to deteriorate. And this deterioration is actually the result of various chemical, physical, and microbiological processes that happen in the distribution system that so far we still don't have a good understanding of. Another important factor that contributes to water quality deterioration in the system is how old our pipes are. Most of our pipes, or much of our pipe infrastructure, is pretty old. Most of the pipes have been placed more than 50 years ago, and in many cases more than 100 years ago. These old pipes, they have significant buildup of biofilms and corrosion scales that are mainly the root cause of many water quality issues in drinking water distribution systems. The bigger issue, though, is that it's very hard, it's very difficult to monitor and manage the water quality throughout the distribution system. And part of this is because of how huge water infrastructure systems are, or water distribution systems are. So I remember working on a project for Austin Water in Texas, and their water system was spanned about 5,000 miles of pipes. And I think that's pretty typical for most US cities to have thousands of miles of pipes in their system. And so it's virtually impossible to monitor the water quality everywhere in the distribution system. And that's part of the reason why many utilities are increasingly starting to adopt smart technologies or smart water technologies in their systems to basically help with monitoring and managing the performance of the system in real time. So ultimately, in a completely or in a fully automated smart system, you would have online sensors that are measuring the state of the system in real time. And then you would also have a protocol for data acquisition and communication, mostly through SCADA systems. And at the same time, you also have models and algorithms that are running in real time to support real-time analysis and decision-making. And that's where my research is focused, particularly on developing novel models and algorithms that can support this smart water systems paradigm. So particularly the key aspects that we try to focus on in my group is how can we develop accurate models to simulate water quality in distribution systems, but also models that are numerically efficient or computationally efficient to enable real-time analysis and real-time simulation and real-time decision making. So today I'm going to be talking about two different kinds of models, mainly numerical transport models, which are basically physics-based models or process-based models. And we developed those in order to simulate and try to understand the fundamental and the mechanistic processes that govern the water quality dynamics in distribution systems. I'm also going to be talking a lot about real-time optimization algorithms. And these are particularly algorithms that we developed for the smart design of different components of the distribution system, and also for real-time decision-making and water quality control. All right, so the first topic of my talk today is going to focus on the optimization of chlorine dosage in distribution systems. So as probably many of us know, in the US, water utilities are required to maintain a minimum concentration of disinfectant residuals throughout the water distribution system. And that's really not an easy task. It's quite challenging, particularly for chlorine-based disinfectants, because they're very active, and so they undergo side reactions with all sorts of organic and inorganic compounds in the distribution system. And that leads to the depletion and decay of chlorine residuals in the system. And so maintaining a sufficient residual is not always an easy task. And water utilities can't just simply increase the chlorine dose if they run into an issue with maintaining chlorine residual, because that in itself leads to a lot of problems with excessive disinfection by product formation. So it's always a trade-off between maintaining sufficient residual, but at the same time making sure that the chlorine doses added to the water are not super high, that would lead to the formation of disinfection by products. And so an important question here is, well, how much chlorine should we exactly add to the water, right? So what is the right dose, or what is the optimal dose that should be added to the water? And in fact, that's only one half or part of the question. The other part is, where should chlorine be added? And that's probably more relevant to larger size water distribution systems. So for small size systems, well, it's pretty obvious. The chlorine is only added at the water treatment plant. For larger systems, because the initial dose added at the treatment plant may not be sufficient to maintain that residual at the very far ends of the system, in many cases, we need to boost the chlorine concentration somewhere in the distribution system. We call that a chlorine booster or booster chlorination system. And so now the other question in the design process is where to place those boosters. So really the design of a chlorination system is a question of how much chlorine should be added in terms of the dose and the pattern, if there should be a pattern, because sometimes we need to dose chlorine at different rates during different times, depending on how the demands in the system look like. And the other part of the question, where should we dose, or where should we inject chlorine in the system? For the design objectives, there's been many objectives proposed in the literature, but perhaps the most common ones are the ones that focus on minimizing the total cost of chlorine injection. So that basically includes two components: the capital cost of chlorine injection, or the capital cost of booster system booster system design, which basically is a function of two components. The first one is how many boosters should be added should we include in the system, or how many booster stations should be included in the design. And then the other question is, what is the maximum injection rate that a booster can inject? And so the higher the injection capacity for a booster, the more expensive we expect it to be. The other component of the cost is definitely the injection cost, which is pretty much the running cost or the operational cost. And this is basically a function of the total chlorine dose that is injected into the system. And so when we're trying to design a booster chlorination system, we're trying to minimize both the capital and the injection costs. And this is obviously subject to constraints on the chlorine concentrations in the distribution system. So we want the chlorine concentrations not to exceed a maximum limit, typically 4 milligrams per liter as the regulations mandate, but most systems try to operate at lower values than that, somewhere in the 1 to 2 milligrams per liter as a maximum concentration. And then the lower concentration, or the minimum residual concentration, the mandates really depend on or vary by state, but the most common one is about 0.2 milligrams per liter, which is pretty much what most utilities try to shoot for, somewhere between 0.2 and 0.5 milligrams per liter of chlorine minimum in the system. So in order to solve this optimization problem, we can develop what we call a simulation optimization technique, or a simulation optimization framework. And in this framework, we basically have an optimization routine linked to a simulation model. The most common model, obviously, is EPANET, which can produce chlorine, or basically simulate chlorine concentrations at all consumption nodes in a distribution system. And then basically how the process works is that you start by proposing a design scenario, and then run the simulation in EPANET for that particular scenario, evaluate the chlorine concentrations, see or calculate where the violations for the minimum and maximum concentrations are, and then evaluate what is the total cost of chlorine injection. And then based on these outputs that you get from the simulation model, you propose a new design scenario. And this could actually happen either by using a simple what-if scenario analysis, or a more advanced mathematical optimization algorithm like the ones we use in research. The problem, though, is that EPANET has its own shortcomings, particularly when it comes to simulating dead ends. That's where EPANET comes really short. So here in this slide, you can actually see two figures. The top one shows a comparison between EPANET simulation, which is represented by the solid line, against field measurements for a distribution main pipe. And then the figure on the bottom shows the same relationship, but for a dead end pipe, which is typically a smaller diameter pipe at the outer branches of the water distribution system. And so for the main pipe, you can see that EPANET does a pretty good job at simulating the field concentrations, whereas for the dead end pipe, the simulation result is pretty much all over the place. And by the way, these figures are straight from the original paper by Lou Rossmann, the famous Lou Rossmann, who developed EPANET. And these are the field measurements that they use to calibrate and validate EPANET. So I guess the first question of this project was, well, we need to understand, why is this the case? Why is EPANET coming short when simulating dead end branches? And how can we overcome this limitation? Can we come up with a model that would provide a better performance or a more accurate estimation of chlorine residuals in dead ends? And in order to answer that question, we first needed to dig a little bit deeper into what dead ends are and where they are located in the system, and what their key characteristics are. So you would typically find dead ends in cul-de-sacs, basically the one-end pipes that are linked to the main body of the network through one junction, but then the terminal junction is closed, as you can see here in the figure. So the terminal junction is not connected to the network. So the dead end branch is only connected to the water distribution system from one end. And what that means for the hydraulics in that dead end branch is that the flow is unidirectional. So the water only goes into the dead end branch, but when there's no consumption, the water just sits in the pipe, or in other words, the water stagnates. And that's a big issue, because stagnation means higher water H, means faster chlorine depletion, means significant growth of biofilms and corrosion byproducts. And these stagnation periods happen frequently, pretty much every night when people are not using their water, the water just sits there. And so we started digging a little bit deeper into the model itself, how the model was formulated in order to try and understand where the approximations are not adequate for dead end pipes. So perhaps the best way to model constituent transport in a water distribution pipe or in a water pipe in general is through using a dynamic 2D convection diffusion reaction equation. And so here you can see on the left side, there's the accumulation term, which accounts for the change in the chlorine concentration with time. And the chlorine concentration itself is a function of the axial and the radial coordinates and time. And then on the right-hand side, you can see the advection term and the diffusion in the axial direction and the diffusion in the radial direction. And then some bulk reaction, which represents how chlorine decays in the bulk flow. An important component of the model is also how chlorine is depleted at the pipe wall, which basically represents how chlorine reacts with biofilms and pipe scales deposited at the pipe wall. And so this is usually presented with a flux boundary condition. So basically the radial flux is equivalent to the rate of wall decay at equilibrium. And then the rest of the boundary conditions are pretty straightforward. So this would be the optimal model to use for a water distribution pipe. But being a 2D dynamic model makes it very, very computationally expensive. And that's why most studies, including EPANET, has tried to approximate that model, make some approximating assumptions to kind of reduce the model into simpler forms that can be more computationally efficient to solve. So the first and perhaps the most common assumption is to get rid of the radial diffusion term. That's because usually in pipes, radial diffusion isn't as important as axial advection and also axial dispersion, as we're going to see later. So radial diffusion is typically replaced with a film mass transfer model, and that's a trick that EPANET has and pretty much all other models for water quality and distribution systems also implemented. But that's not really the issue here. The issue with EPANET is that it ignores the longitudinal dispersion term in the equation. And it basically assumes that the radial velocity profile in the pipe is uniform. Now, if you know fluid mechanics, you probably know that this is only a good approximation for a turbulent flow pipe, where the flow is purely plug flow. But in a laminar flow, that's really not the case, because the velocity profile in a fully developed laminar flow is parabolic, and that causes or leads to the fact that constituents moving along the streamline or closer to the center line to be moving faster than the ones moving near the pipe wall, and that's what causes hydrodynamic dispersion in the constituent transport. And so that was the first thing that we kind of included in our model. So I guess now is the right time to introduce the model that we developed, which is WU-DESIM, which is short for Washington University Dead End Simulation Model. It's named Washington University because I developed it when I was a graduate student at WashU. So the key difference in the transport equation is that EPANET uses uses an advection reaction equation, whereas WU-DESIM uses an advection dispersion reaction equation. Makes it more suitable for laminar flow, which is more common in dead end pipes where the flow is actually very slow. The other issue with EPANET is that the way water demands are simulated in EPANET, it's not really a fundamental issue in EPANET itself, but rather in how water demands are accounted for in EPANET. So typically, when we assign demands in an EPANET model, we use generalized demands or aggregated demands or average demands. So basically, you would take the water demand over a period of 1 hour or 2 hours and average it. And that makes the simulation a lot easier and more computationally efficient. And is perhaps, again, a pretty good approximation for turbulent flow in large transmission mains. But is probably not a very good approximation for dead ends, because we can't take the average over the demand during a period where there's stagnation. We really need to accurately account for all the stagnation periods that happen, because that's when most of the water quality deterioration takes place. So in order to overcome this limitation, what we did was we developed a stochastic generator that basically simulates water demands on a second-by-second basis. So it uses a dynamic Poisson pulse process. It basically assumes that water demands are a Poisson process with a non-homogeneous rate, and then each water demand pulse is characterized by a certain intensity and a certain duration. And then we sample those based on log normal distributions for the duration and the intensity of the water demands. The third issue, and perhaps the most important one with EPANET, is the spatial aggregation of water demand. So in addition to temporal averaging, there's also a different kind of averaging that takes place in EPANET, which is a spatial approximation or spatial aggregation, or sometimes people call that skeletonization. So instead of really simulating each and every single demand point in a distribution system, we tend to lump them up into kind of major consumption nodes. And so again, this is a pretty good approximation for main transmission lines, because the key purpose of main transmission lines is to move water downstream to the downstream sections of the network. So the consumption that happens on the pipe itself is not significant compared to the flow that goes through the pipe to downstream sections. But for dead ends, that's a pretty bad approximation, because in dead ends, all the consumption happens on the pipe. So you can't really lump up all the flows, or sorry, all the demands and just assign them to the terminal node. And if you just quickly try to see how that affects the flow velocity and the residence time of the pipe, you would see that this approximation actually overestimates the flow velocity. So it really simulates faster flows than what happens in reality. And at the same time, significantly underestimates the residence time. So the residence time that you're simulating in the model is significantly shorter than the real residence time. So in other words, the water age in the real system is significantly longer than what is being simulated in the model. So it's really not easy to break down each pipe into a bunch of segments and try to account for each one of the consumption nodes, because from a pure practical standpoint, that would create a significant computational overhead for the numerical solution of the advection dispersion equation. And that's why an important part of this work was trying to find if we can approximate this single segment model, or sorry, approximate the multi-segment model, but at the same time retain the computational simplicity of the single segment model. And the idea that we came up with was, well, what if we start by non-dimensionalizing the transport equation, and then try to correct the dimensionless parameters that control the transport in the dead end pipe. So in short, these would be the Reynolds number dictating the flow regime in the system, and obviously the residence time, the Piclet number, which controls the ratio or the effect of advective transport compared to dispersive transport, and the Dam-Kohler number, which really controls the extent of the reaction taking place in the system. And then with a few approximations, we were actually able to theoretically derive a set of closed form correction factors for the three dimensionless parameters that are a function of only one variable, which is the number of segments for the equivalent of the multi-segment model that we need to correct for. And by running a lot of test cases and a lot of scenarios for different pipe diameters, different pipe lengths, different reaction coefficients, and different flow rates, we actually found that these approximations, or these correction factors, do significantly reduce the error in the single segment model, while at the same time maintaining the computational simplicity of the single segment model. So as you can see here in the figure, on the y-axis, you have the root mean squared error percent for the model with correction, and on the x-axis you see the error without correction. And so you can see that all the points for all the different test cases are significantly below the 1-to-1 line, which means that the errors for the simulations with the approximations with the corrections have significantly less errors than the simulations without the corrections. So the last step was to develop a numerical algorithm or numerical scheme to solve this problem. And we actually looked a lot at different numerical methods. And perhaps the one that was most appropriate for this particular application was a mixed Eulerian-Lagrangian numerical scheme. So in this scheme, you basically split the transport equation into two steps, a Lagrangian step and an Eulerian step. In the Lagrangian step, you solve the advection component, with the advection and the reaction component, in this case using the method of characteristics. And then in the Eulerian step, you solve the dispersion and diffusion component. And the beauty of splitting the operators into two different steps is that the numerical scheme is stable for all different kinds of flow regimes. So that would mean that the numerical scheme would be stable for a turbulent flow condition and for a laminar flow condition, not just for a laminar flow condition. And although we know that dead-end pipes normally operate under laminar flow, there are some occasions in which the flow steps up into the turbulent territory, and we wanted the numerical scheme to be stable under these conditions as well. And so when we started to compare the results of EPANET against WU-DESIM, you can actually see the results here in these two figures. So on the left side, we see the comparison for the fluoride tracer, and on the right side, we see the comparison for free chlorine. So fluoride tracer is a non-reactive tracer. It's a conservative tracer. So this can actually tell us whether the transport description in the model are accurate or not without accounting for any reactions. And as you can see here, so the dashed red line is the EPANET simulation. So this is the one that I showed before, but basically regenerated from the model. And it's pretty inaccurate when compared to the field measurements, whereas WU-DESIM has a pretty good or a pretty accurate simulation of the field measurements. And you can see that the root mean square error percent for WU-DESIM for the case of fluoride is significantly less than EPANET. We also see the same thing with free chlorine, although the error for free chlorine for WU-DESIM is still high. And part of the reason why this is the case is because we still use the first order decay kinetics, which are known to be inadequate. So that was actually a second part of the project that I'm not going to talk about today, which was developing a more advanced kinetic model for chlorine decay reactions in distribution systems. But for now, we thought that was good enough. We at least developed a model that was significantly better than EPANET in simulating dead ends, which are known to be problematic, particularly problematic from a water quality deterioration standpoint. We also wanted to see how would that affect the results of the optimization process. So we used this mid-size water distribution network. It's widely known by the name Seatown, but it's based on a city in Israel. I'm not going to say the name of the city because I don't want to get into trouble, but this is a relatively mid-sized network with about 400 nodes and about 400 links. What makes this network particularly useful for our application is that about 1/4 of the links are actually on dead-end branches. So that would actually give us a pretty good indication of how both models, WU-DESIM and EPANET, perform when we use them for chlorine booster optimization. And so I guess the key result here that I would like to highlight is how using EPANET resulted in a significant amount of violations in the dead ends. And by violations here, I mean that the chlorine concentration was below the 0.2 milligrams per liter minimum residual requirement when EPANET was used for the optimization. Whereas for WU-DESIM, the percentage of dead-end violations was significantly less than that, about 1/3 of this value. And so the reason why this is the case, you can actually see that pretty clearly when you put a simulation of EPANET versus a simulation of WU-DESIM of a dead-end pipe. You can see that in most of the dead-end pipes, the chlorine concentrations simulated by EPANET are significantly larger than the ones produced by WU-DESIM. And that is actually a direct result of the underestimation of the residence time in EPANET, because if you remember what I said about spatial aggregation, is that it results in significantly or severely underestimating the residence time. So in other words, the water age is significantly higher than what EPANET is simulating, which means that chlorine is allowed to deplete for a longer period, resulting in lower concentrations, as we can see in WU-DESIM. And if you also track the error or the deviation between EPANET and WU-DESIM, as you can see in the figure on the right, you can see that the root mean square deviation between the two models, it drops sharply right at the 2000 mark for the corrected Reynolds number, which means that this approximation is actually pretty accurate. The spatial aggregation approximation is actually pretty accurate for turbulent flow pipes, but not very accurate for laminar flow pipes. So what that tells us is that we probably don't need to run WU-DESIM for all the dead ends in a given distribution system. If we can simply check what the dominant flow regime in that pipe is on average, we can actually figure out if we can just use EPANET for it, or if we need to go to the more complex and computationally expensive WU-DESIM model. So the second part of my talk, or the second project that we've been working on over the past few years is optimizing the placement of water quality monitoring stations in a distribution system, or optimizing the placement of water quality sensors in a drinking water distribution network. So the majority of the previous studies that looked at this problem, and there has been a significant amount of work that went into trying to look at where would be the best place to install water quality sensors in a distribution system. But the majority of these studies focused on contamination event detection, right? So they propose different sorts of optimization objectives. They're all focused on public health, minimizing public health impacts of contamination events, like minimizing detection time, so how long it takes for the sensors to pick up or to detect a contamination event in a distribution system, or minimize the affected population. In other words, minimize the total volume of water consumed that has the contaminant. Or try to maximize the detection probability. So just make sure that at least one of the sensors that we placed in the system would be able to detect the contaminant, the injected contaminant. And while all of these are pretty good objectives, they're really overlooking a very significant and a very important purpose for water quality monitoring stations, which is having a good observability over the system under regular operating conditions. So yes, it's important to detect contaminants, but we also want to have an idea of what kind of water quality states we have in the systems. And we need to have a pretty good understanding of the dynamics, the water quality dynamics in the distribution system. And so that was the key focus of this part of the project, is to develop a sensor placement optimization algorithm with the design objective to maximize network-wide observability of water quality indicators. So particularly in this case, chlorine concentrations in the system. So what I mean by observability is, if you look at the figure here, this is basically a schematic of a very small distribution network with one source, one pump, and one tank. And so if we install water quality sensors at junctions 21 and 12, we're going to have pretty accurate estimates of water quality indicators at these two junctions, because these are the direct measurements of the sensor. But what about the other locations where we don't have sensors? Well, I guess we can use a model to estimate the water quality states at these sensors, or at these locations. And what I mean by water quality states is basically chlorine concentrations for this particular application. So in order to do that, we need to develop a state estimation model, a model that we can use to estimate the chlorine concentrations in locations where we don't have sensors. And we also want that state estimation model to be as accurate as possible. So we want to strategically place our sensors to maximize the observability of the system, or to minimize the state estimation error. And if we are able to do that, we can actually, if we are able to have accurate state estimation, that would fit right into a robust real-time decision-making algorithm, because then the sensors would be giving you readings on the states of the system. The state estimation would basically tell you how the rest of the system is behaving, and then you can make good informed real-time decisions on how to manage and how to operate the system. So if, for example, you want to activate a booster or shut down a valve, you would know exactly what the impact of that would be on the system in real time. So, well, that's not really as easy as it sounds, because if you think about a large water distribution system, trying to find the best place to install a sensor is very computationally expensive. So just considering the mid-sized network that I just showed, if we have about 500 potential locations to install 5 sensors, that means we're going to have to run through about 0.5 or 0.2 billion, sorry, 0.2 trillion iterations to find the best location for all these 5 sensors. We can use some kind of a smart judgment to reduce the search space, but that's not always going to help. So we still need to develop a scalable model that we can use for any system, regardless of its size, to find where to place the sensors. And the system or that framework should also be efficient, so that if at any point we needed to change the locations of those sensors in response to an event, we can do that rapidly or quickly. Another thing to keep in mind is that when you do the optimization, you're going to have to assume a certain hydraulic scenario. But hydraulics and distribution systems are very uncertain. They change significantly from one time step to another. And so if you want to strategically place your sensors, you're going to have to sample through a lot of hydraulic scenarios, which adds more to the computational complexity of the model. So the numerical models that I've talked about so far, EPANET, WU-DESIM, they're very computationally expensive to evaluate. And more importantly, they're all black box models because they're numerical models. So we don't really have access to the internal of the model, and we can't really use it for state estimation unless we do some kind of an inverse modeling or inverse optimization, which in itself is very computationally expensive. And so to overcome this limitation, what we wanted to do is to derive a state space representation of the water quality dynamics. And in a second, I'm going to explain what that actually means. And then we wanted to use that state space model or state space representation to find the best place to locate, or the best locations for sensor placement in order to maximize the observability of the water distribution system. All right, so what is a state space representation, or what is a state space model? In its most simplest form, it's basically a linear relationship between the state of the model, or the states of the system at time t+1 as a function of the states of the system at time t. Now, the formulation that we were trying to derive here was to have a linear model in which the state space matrix, the one that basically lumps up all the hydraulic information and all the node link connectivity information, is a combination of linear equations. And basically, if we are able to do that, we can use an advanced algorithm for state estimation like Kalman filter, which is exactly what we did. And that would speed up the optimization process significantly. And so states here means chlorine concentrations. For this particular application, it means chlorine concentrations in all the nodes and all the links in the system. So that includes chlorine concentrations in all junctions, reservoirs, tanks, pipes, pumps, and valves, right? So I guess the key idea here is, if we are able to sample a subset of these states, can we estimate the rest of the states, knowing what the model looks like, the state space model looks like? All right, so we had a lot of work to do because there's no such model, right? A such model for a water distribution system, a state space model, doesn't exist. And so in order to derive this model from scratch, we had to go again back to the fundamentals and try to derive everything in a matrix form from scratch. So we started with mass balance in the different components of the system. So mass balance in pipes, that was again approximated with a 1D advection equation with a first order reaction. And then the trick here was picking a numerical scheme that can be written in a matrix form. And so that basically ruled out all sorts of implicit numerical schemes, and we only had to focus on explicit numerical schemes. So for this particular application, we chose Lax-Windroff, which basically gives the concentration at any segment in the pipe at t+1, knowing the concentration at t at the same segment and the segments right after and right before that particular segment. And so, if you're good with math, you can actually imagine now how that would look like in a matrix form, because then basically you could lump up all these coefficients in a matrix and find a concentration at all segments at time t+1, knowing the concentrations at all segments at time t, and also knowing the spatial discretization matrix. The other component of this formulation is the node link connectivity, because if you look at the first segment in the model, sorry, in the pipe, this gets mass straight from the node or from the junction right before it. And then the last segment in the pipe sends the mass to the node right after it. So this node link connectivity is what ensures mass continuity, that the mass that goes into the junction moves to the next pipe and then moves from the next pipe to the next junction and through the next pipe and so on and so forth. So that second part, the second component of the matrix form represents the node pipe connectivity. So what nodes are linked to what pipes in the system. And then the second task was to develop a similar representation for mass balance in junctions. And for that, we had to develop a model for this. So the simplest model that we could come up with was complete and instantaneous mixing. So basically, assume that for any junction in the system, all the mass or all the flows that go into the junction are completely and instantaneously mixed. And then the concentration leaving the junction is uniform in that sense. And that includes the concentration of all the demands at that junction. So you can see this formulation here for the demand or the flow in link Ki, which is an inlet link to junction I, and then the demand or the flow in link Ij, which is an outflow pipe from junction I, and then Di, which is the demand at the junction itself. And again, we were able to lump all of these up in a matrix vector form for all the junctions in the system, using again the same notation for the junction link connectivity and junction connectivity. And then the last part was to develop a mass balance representation for tanks in the system and for reservoirs in the system. So for tanks, we use the CSTR representation. So basically, again, complete and instantaneous and homogeneous mixing of all inflows to the system, and then homogeneous outflow from all tanks. Another assumption that we made for reservoirs is that they serve as chlorine sources, so they have constant concentrations, and we actually know what these concentrations are. And so the final step for developing the model was to basically lump up all these matrix vector equations into one large system of equations, which is basically the state space model that I introduced earlier. So essentially, each one of these small A's matrices represents either a connectivity matrix between a pipe and a link, a tank and a pipe, or it represents spatial discretization that represents the mass balance, numerically represents the mass balance in pipes.
I just want to pop in and say we have a big queue of questions if you want to wrap up shortly here. Just to, yeah, lots of interest.
Cool. All right, so the last part was to basically use a Kalman filter, which basically is an algorithm that takes in sensor measurements at different time steps and the state space model, and then through an iterative process, quite efficient iterative process, I should say, estimates the system states at all time steps. So that basically is the end goal of this framework, is to estimate the system states at all time steps, knowing what the sensor measurements are and what the state space model is. And so the final step was to formulate the optimization problem. So we're basically looking for the set of optimal sensor locations for a given demand distribution, which is basically a subset of all the nodes in the system, with a maximum constraint on the maximum number of the sensors that we can have in the system. And so the objective was, again, to minimize the state estimation error using at most R water quality sensors. And that was done using the Kalman filter. So basically, because we know that the actual water quality states, we can compare those to the Kalman filter estimates and calculate the error associated with each sensor placement design. And then we can actually find what the best sensor placement design would be. Just an important thing to note, we have to account for accessibility and feasibility restrictions when we place those sensors. So we can't just place them anywhere. We have to be aware of where or what are the possible locations where these sensors can be installed. So just just two quick highlights of the results from this work. The first one is that the simulation results or the optimization results were very sensitive to the demand scenarios that we assumed. So we tried a bunch of different demand scenarios. This is just a sample of 3 different demand scenarios. And each one of the demand scenarios came up with a completely different result for the optimal sensor location. So a good understanding of the demand profiles and the demand patterns of the system is very significant and very important. And if there is uncertainty in the demand profiles, it has to be accounted for in the optimization process. And the beauty of the state estimation model is that it actually explicitly accounts for that uncertainty quantification or uncertainty inclusion in the system. The other important component, or the other important conclusion of this work was that the objective function had a very strong submodular property or diminishing returns property. So in other words, what that means is if you add one more sensor to the system, or to a system of 2 sensors, the value of adding that sensor would be less than adding 1 sensor to a system with 1 sensor. So in other words, the more sensors you add to the system, the less the value of adding more sensors to the system are. That's what we call diminishing returns. So basically adding more and more sensors isn't always a good idea. At some point, you would have enough sensors. And adding more sensors wouldn't really increase or enhance the state estimation of the model. The last part is that when we compared the results of the optimization model with random placement of sensors, we actually found that the optimization algorithm that we developed produces significantly better results compared to random sensor placement. So on average, a factor of 100 for this particular simulation of 10 different random realizations was achieved, which was a pretty good result. So I guess I'm going to have to wrap it up at this point because I understand we have a lot of questions, as Elena said. So yeah, I'm happy to take any questions.
Great, amazing. I'm going to try to condense as many of these as I possibly can, and assume you'll have your contact information up on a last slide or something if we have follow-ups, because there were quite a few, and I think a lot of them kind of leaning towards implementation. So I think you may have gotten to this in the last couple of slides, but lots of interest in leaks and how to account for them. Do you have to understand how many leaks in your system, where they are, that sort of thing, to be able to model this, or is that part of the demand uncertainty, or the flow uncertainty that you're talking about in this last bit that's sort of accounted for?
That's exactly right. So leaks are not usually explicitly accounted for in models. So if you want to account for leaks, you're going to have to do that through an uncertainty framework. There has been some studies that looked at how different leaks influence water quality dynamics in distribution systems. And in many cases, leaks aren't a big concern from a water quality standpoint, unless there is a concern of cross-contamination or contaminant intrusion through cracks at junctions or in the pipes. But as far as our research is concerned, we didn't really look much into how leaks would affect the results of the optimization and the analysis.
Great. For this sort of model, does the placement of the sensors depend, and I'm really thinking about the applicability of the model overall, depend on the kind of contaminants you're monitoring? Like, would this just be for limited to sort of chlorine? Yeah, or
no, so that's actually a very good question too, because so the framework itself is general. It could be applied to any kind of water quality monitoring station or any kind of water quality indicator that we're interested in monitoring in a distribution system. We chose chlorine because we were more interested in the regulatory side of things. So we wanted to monitor or observe chlorine dynamics in the system under regular operating conditions. But the model could be extended to other kinds of contaminants if the purpose is for contamination event detection, and it would work in the exact same way. It won't really change anything except for the reaction dynamics. That's about it.
Well, that's really interesting. I mean, thinking about this, we're doing water quality monitoring in the Chicago River, completely different from, pipes in a water distribution system, but similar complex challenges. There's probably a follow-up there. And then in terms of accessing the data for folks that are running, managers of the system, a lot of this is operational. Is there also any utility to having, sort of end user consumers have access to that data, or is that a completely, this is mostly just thinking about the risks and trade-offs, I guess, and the potential for making some of this information more public. Have you thought that through?
So exactly what kind of information are you thinking about? So
Yeah, I guess just ask the question.
because water infrastructure systems are sensitive, critical infrastructures. So open access to all kinds of data for water systems is probably not a great idea, because if it falls into the wrong hands, bad things can happen. And I've seen this many, many times working with water utilities. They're very protective of their data, and
Absolutely.
sharing data or really releasing data from their databases to our databases is a pretty long process that includes a lot of steps. So I don't know. I don't think. Yeah.
I think one of the links was to sort of consumer placement of sensor, like thinking about the end user.
Oh, I see. So what if we can place those sensors at consumption locations,
point of consumption,
right? At the point of consumption. Well, that would be ideal if we can develop cheap sensors that are cheap enough so that we can install many of them throughout the system. That would actually make the state estimation problem a lot easier and a lot more accurate, because then the number of states that you're trying to estimate, the number of unknown states that you're trying to estimate is going to be less, and so the accuracy would be higher. So yeah, that would be a great contribution, I guess.
Mm-hmm. Great. Well, I think we are out of time. I know we probably left some questions on the floor here. Did you have a slide with your contact information you wanted to put up briefly, or drop it in the chat?
I can drop it in the chat. So.
That would be fantastic, because I think I get the sense that there are quite a lot of questions about, just the validity, how you compared. I think further questions on how you compared the two models and the results, as well as just questions about adoption and use and reliability of the sensors. But I really thank you for a terrific talk. I'm going to go back now just to finalize our wrap up the year. We've got a quick audience poll up on screen. We'd love to hear from you if you thought this was a great event and talk. We'd love to hear your comments and questions for making them even better next year. I also want to put in a plug for the next Third Coast Water Seminar, which will be the first in January of next year, where we'll have Dr. Amy Childress from University of Southern California on systems for potable reuse and desalination. Back to a topic that we've had with some frequency here at Third Coast, talking about desalination and water reuse. So really excited to have another outside speaker in, and wish everyone a wonderful holiday season. And thanks so much for tuning in this year, throughout the year. Really look forward to a action-packed event year here at the Third Coast, but also for current overall next year. So thanks again for being with us today. Thank you to Ahmed. Thank you, Brian. Thank you to all the other wonderful organizers of the Third Coast Water Seminars. We are super excited to have you, and look forward to.
Thanks, Elena, for inviting me to.
Absolutely.
Talk today.
Yeah, of course. It's a total pleasure. All right. Take care. Thanks everyone for tuning in.